Hey, greetings and welcome. We're continuing our look today at probabilities of compound events, and we're going to consider some OR cases, the probabilities of this or that happening. And let's consider the following problem. All right, probabilities of compound events. If I'm rolling a six-sided die, so roll 1d6. I can use that lingo. You guys are all nerds here. I'm among friends. Roll a 1d6. What is the probability of rolling a 2 or a 5, let's say? Now, you might be able to think of what the sample space is here. You're like, okay, that's rolling a 1d6. The possible outcomes are 1, 2, 3, 4, 5, or 6, right? That looks like a 56, a little too much. And you might look at that and say, well, how many of them are either 2 or 5, right? And you would have said, well, there's a 2, there's a 5, so there are 2 out of 6 outcomes, right? And then you'd reduce that probability to 1/3. But consider this. What is the probability of 2 outcomes on this, and what is the probability of 5? Not the probability of 2 outcomes, but what's the probability of rolling a plain old 2? Right, there's a single 2 there, so that's a 1 out of 6 chance. And the probability of rolling a 5 is a 1 out of 6 chance. So I want to point out that the probability of 2 or 5 occurring, I could actually have thought of it as this, as the sum of these two probabilities. I could have said 1/6 plus 1/6 was equal to 2/6, or 1/3. All right, and the reason I can do that, all right, for OR problems, at least this particular OR problem, is that I can never roll something that is both a 2 and a 5 at the same time, right? It's either a 2 or a 5. There's no overlap between those two things. So let me talk about why I could just straight up add those probabilities. Is because these two events, rolling a 2 or rolling a 5, those two events are called mutually exclusive. And mutually exclusive means that both outcomes cannot simultaneously occur, or cannot occur simultaneously, maybe. Simultaneously, there we go. All right, so mutually exclusive events, if I was to draw a Venn diagram, all right, where say this orange box was all possible outcomes. So in the case of the die rolling, that would have been the 1, 2, 3, 4, 5, 6, all possible outcomes. All right, and then some of those outcomes, all right, were event 1. That's kind of dark-ish there. I'll keep the dark blue circle, but I'll just call this event 1, right? And then another set of outcomes is event 2, and there's no overlap between those two things, right? So in the case of our die rolls, 1 would have been in the general outcome, but not in any of those circles. 2 was event 1, 3, 4, 5 would have been in here, and 6 would have been in there. And I never could have rolled both a 2 or a 5. And because those events were mutually exclusive, and I was considering the OR probabilities there, I could simply just add this area and this area, or add those two probabilities and put it over the total possible outcomes, and that would give me the probability of either event occurring, right? And with the concept of either, right, or the OR word being used there, I'm considering both of those as successful. And that's why that was able to work. So So this is the idea, the probability of mutually exclusive events. I'll just call it M dot E, events. Looks like this. So if two events, if A and B are mutually exclusive, then I guess I could throw an if in there. I might as well try to write some sort of a sentence, even though I'm a mathematician. If A and B are mutually exclusive, then the probability of A, or B, sorry, occurring is equal to the probability of A plus the probability of B. Right? So that's the probability of mutually exclusive events. And I want to point out, yesterday we talked about the probability of two events occurring at the same time, the probability of A and B occurring. So when we had and, what operation did we have between the probabilities? What were we doing yesterday? We were multiplying, right? So if this was an and word, you'd multiply. If it's an or word, you'd add. Okay, so that's a little bit of a comparison between those two things. So let's do an example. So if I'm drawing, let's say, two cards from a deck, what is the probability of getting two face cards or getting two, let's say, tens? So before I can actually figure this out, I have to ask the question, could I ever get a face card that is also a 10? No. All right, that doesn't happen. Okay, so these two events, getting two face cards or two tens, those are mutually exclusive. So now I can find their independent probabilities, right? Or each probability individually, using the word independent there a little loosely. So probability of two face cards I'll find. So that would be a combo of how many face cards are there? Yeah, I think there's 3 face cards per suit, 4 suits, 3 times 4 is 12, yep. And then I would also find the probability of 2 tens. And how many tens are there? 4, there's 1 in each suit. Right? So I could find both of these probabilities on their own, and then I'm just going to add the answers together. So let's see, so 12 combo 2 is 66. And they have the same denominator, which is nice. So since I'm adding them together, I'm going to be adding fractions. So even though I might be able to reduce this in advance, I actually specifically won't want to. Combo 4, 2, if I remember, was 6. So 13, 26, and 66 over 13, 26. Let's see. So I will just merely take both of these and add them together. So that's going to be 66 over 1326 plus 6 over 1326. So that's 72. And I can reduce that, I believe. Looks even. By the way, this is roughly a 5.4% chance of occurring. That becomes 12 over 221. So that's the idea of those probabilities independently, individually occurring. All right? And because there was no overlap, I was able to just straight up add those together. All right, so not too crazy. So let's talk about what if our events are not mutually exclusive but are inclusive. So inclusive events, what I'd mean by that, are two events that can occur. They don't have to, but they can occur at the same time. T-I-M-E, bam. So my Venn diagram picture for inclusive events would actually look like a really classic Venn diagram. So I would have, let's see, I think I had my blue circle the first time, and then maybe it was a pinkish circle. So I'd have event 1, event 2, and there's some commonality between them. All right? So this is a possible arrangement of that. So two events that can occur at the same time would be like, say I'm rolling a die, 6-sided die. What's the probability of rolling an even or rolling a prime? So let's say I have even and prime. So let's see, prime numbers are like 1 is prime, 2 is prime, but 2 is also even, so 2 is an overlap. 3 is prime, 4 is not prime, 5 is prime. And then even numbers that were not prime would have been like 4 and 6, right? So there was some overlap between those two things, right? So it's also possible, maybe I'll draw a second case of this, to have inclusive events that are kind of like an egg in its yolk. Let's see. Let's say I've got this and this, where the purple events are a subset of the other ones. But that still is considered a type of inclusive. Can you guys think of a situation that's like that? Say, what if I had red cards and face cards? Well, actually, wait. No. Face cards would also have had their own space of non-red face cards. So let's see. Let's say I had red cards and then the Queen of Hearts, or just heart cards are a subset of red cards. Sorry, right? Something like that. Yeah. So I'll just say hearts. There we go. Bam. Problem solved. So half of the red cards would be heart cards, but there are no heart cards that are not also red cards. There we go. Whew. I didn't think that one out very well. Right, so that also can occur. These are also types of inclusive events. So the overlap in this case is the entire second set. The overlap here is a portion of that set. And the problem is that now, what do you think I would do if I wanted to find the probability of rolling an even or a prime? How could I calculate that if I have probability of even or prime? Yeah, so I'd add the probability of even, the probability of prime, and then I'd have to subtract the probability of both occurring at the same time. So I'd have to subtract that overlap, like you were saying. And that's exactly it. So let's see. Let's write that down. Probability of inclusive events. So if A, all right, let me write the if A and B are inclusive, then the probability of A or B occurring is going to be the probability of A plus the probability of B minus the probability of both, all right, A and B occurring, right? So I could use both. I could describe that as A and B occurring simultaneously, right? Is the idea. So the problem we had that kneecap question the other day, where it was what's the probability of selecting a van or selecting a black car, and we realized that we had the overlap in the cars that were both black and vans. Which, by the way, black van, that's just like the sketchiest vehicle ever, seriously. But we had to subtract the overlap because we accidentally would have counted it twice if we merely added those probabilities together. All right? So, let's do an example of this. So let's consider the cards again. So what's the probability, let's say drawing, let's do 3 cards this time. So what's the probability of drawing, let's say, all 3 diamonds? You hate cards? Yeah. Yeah, it does take some familiarity with the concept for sure. So let's say I'm drawing diamonds or face cards. All right, all 3 diamonds or all 3 face cards is what I'm considering. So, first of all, are these events mutually exclusive or are they inclusive events? And how do you know that? Because a diamond face card exists, right? So, let's find the separate probabilities first. So, probability of all 3 diamonds. How many diamond cards are there? 13, because that's 1 suit. And I'm selecting 3 over combo 52, 3. And let's see, probability of face cards. How many face cards are there? 3 per suit. 4 suits, so that's 12. And how many are both? I'll just write both. How many diamond face cards are there? 3. This diamond is 1 suit, and there are 3 face cards per suit. Okay? So let's see. 13 combo 3 is 286. I guess I can figure out 52 combo 3 at the same time. Bam. 221 hundo. Wow, 221 shows up a lot in these. It's interesting. 12 combo 3 is 220 over 221 hundo. And 3 combo 3. Does anyone know that off the top of their head? It's 1. There's one way to pick 3 people out of 3 to form a group of 3, right? Right. So this is actually a really unlikely chance of me drawing all 3 cards that were not only face cards but were also diamonds, right? That's what's that in poker? Is that a straight? I mean, or that's part of a straight, and that's royal flush. Is that? I don't know. I don't know enough poker tricks, I guess, or concepts. So to figure this out, I'm going to add these probabilities, and subtract this one, the overlap, right? That's the idea. So 286 over 22100 plus 220 over 22100. And then I have to subtract the overlap because we counted that one situation one too many times. Right? So let's see, 286 plus 220. Is that 486 plus 2506 minus 1? Is that 505? Is anyone double checking my math here? 220 plus 286, yeah, okay, I got that right. So 505 divided by 22100. There's a 2.28% chance of this occurring, and as a fraction, my answer is 101 out of 420. Right? So there we go. So that's the idea for that. Let me look at one more situation. This one, for those of you who are currently present, I might not have you write this down because it takes a long time to write this table down all the time. It's on page 861 though, so it's a good page to know for all the times these problems show up. Oh, I need blue. Paste. Here we go. So here's the whole table is a sample set of the possible die rolls of two six-sided dice. And let's say for rolling two dice, let's say I want to find the following probability. What is the probability of rolling at least 1, 2, or a sum of 7? Not quite the situation they have there, but that's fine. So my question is, are these events inclusive or are they mutually exclusive of one another? Inclusive. How do you know they're inclusive? Because 2, 5 is a situation that adds to 7 and has a 2 in it. Okay? So the probability of at least 1, 2, I'd find that probability. We'd find the probability of sum 7. I'd find that. And then I'd find the probability of both, because they are inclusive events. So at least 1, 2, let me highlight which ones those are, is the row that happens to already be highlighted here. Right, those are all successful for having at least 1, 2. I didn't say exactly 2, so that means I do allow 2, 2. Right, so the probability of at least 1, 2 is 6 out of 36. Right? All right, the sum of 7. Let's see, that's 6, 1, 5, 2, 4, 3. That's this whole diagonal. I feel like I'm doing like a word search here. Right, is a sum of 7. How many possible combinations give me a sum of 7? Actually, also happens to be 6 out of 36. And then, how many were both?
2, 5, 2, or is that the same?
Oh, you're right. Good catch. I didn't notice. Oh, wait a minute. Were we wrong with this 6?
Yeah, a lot of other 2s.
Yeah, we got all these other 2s. Wow, this is a doubly complicated situation. Aha. All right, here we go. Whoop, 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 whoop. All right. Aha, good catch. So at least 1, 2 itself was a situation where I had to consider the overlap. Right? I could have actually phrased this as probability of first die 2 plus the probability of second die 2 minus the probability of both. We could have actually done that. That's craziness. This was like a nested one. So how many were there? There was first die 2 is 6 plus second die 2 was 6. Yeah, how did I miss that entire column? Good save, friends. And then one of them was both, right? 2 comma 2. So I had to get rid of that. So this probability is 6 plus 6 is 12 minus 1, 11/36. Okay, aha. All right, sum of 7. There we go, there we go, there we go. Yeah, I didn't even look down at the columns there. Is just straight up 6 out of 36. And then the probability of both occurring, you're right, 5, 2, and 2, 5. There were 2 out of 36 that did that. So, to find this, I would do 11/36 plus 6/36, and then minus 2/36. Right? So 11 plus 6 is 17, minus 2 is 15/36, which I believe both of those are divisible by 3, so that's going to be 5/12 is the final overall answer. Right? Is the probability of that situation. Wow, so that one ended up being a nested inclusive probabilities problem, but that's fine. That's fine. I just wanted to point out that you could have weird, crazy situations like that. So it's a good thing I didn't say sum of 6 or 7, because then that would have been like doubly nested. But okay. Well, thanks for watching, internet friends. Have a great day. Bye-bye.